Okay, day 10. Things are starting to get a bit harder. Our input today is a grid of characters, and these characters form a pipe. Now we've got a description on what each character means. The first one is just a vertical pipe, the other is a horizontal pipe. Then we have an L formed, a J formed, 7 is west and south, and the F is south and east. If we draw our first example, it actually looks like this. There are also some examples that are a bit more difficult, like that one, but the shape of the pipe is actually like this. Now the input also contains a lot of pipes that we don't actually need. There's always a start point inside our input, and that start point can go to every direction, so we don't actually know what shape the start point has. And if we look at that example, you see our start point is here. And now for building up the grid, we will use a breadth first search. We will start our current points. At that moment, it's only the start point. And for every point, we will look which connection it has. So we will look at J first, and J can go up and left. And we will look at that one as well. And this one can go up and down. We will have our new cur, J and I. Assign that to cur and just continue that loop. In the first iteration, we will start here. In the next iteration, we will go here and here. The iteration after that, we will check here and here. Then we will check this one and this one. Then we will go here and here, here and here, here and here. And now both will point to that one. And we've built up the pipe completely. For calculating the result, we actually need to know how many steps along the loop does it take to get from the starting position to the point farthest from the starting position. And once you've built up your loop like this, you can do it in two ways. Either you just count how many items there are and divide it by 2, or the other solution is, when doing the breadth first search, just store how many steps you needed to get to the last point, and the count of steps is the solution for part 1. And part 2 is actually a lot harder than the first part. Now that we know the loop that we have, we need to find how many nodes are enclosed by the loop. And the interesting thing is that one doesn't count because you can actually escape between those two pipes. So I went for a raycast solution. Solving that with a raycast is actually quite trivial once you know how it works. So for example, let's say we have a circle. Now we want to know, is a node we're currently looking at inside the circle? So let's say we look at that node in here. We'll now use a raycast, so a line that's going into one direction to figure out whether it's inside or outside. So if we go to the upright, we will draw a line here. Actually, there's only one intersection between our circle and the line we just drawed. And if we look at one that's outside of the circle, draw a line here. We see there are 2 intersections. If we look at that one, draw the same line here, we see that there's no intersection. And that's how that algorithm works. You use a line that actually goes until infinity, or in our case, until we exceed the coordinates that we started with. And then just count how many intersections with our pipes there are. If the count is even, like in our blue examples, the point that we're looking at is outside the polygon we're testing for. And if the count is odd, like in the red one, it's inside that polygon. There's one thing that makes the whole thing a bit tricky. If we have a point, let's say it's here, and then we draw the line that just touches our circle but doesn't intersect with it, we only have one intersection, but the point is actually outside. So we need to make sure that we handle that case properly as well. In our example, we do that by ignoring some edges, but you can find that in my GitHub repository as well. Let's do another quick example, which is a bit more difficult maybe. And draw a line here. The angle of the line doesn't actually matter that much. So we have 1 intersection, 2 intersections, 3 intersections. So the amount of intersections is odd. That tells us that it's inside. If we, for example, take that node here, draw a line all the way up here. We have 1 intersection, 2 intersections, and the number of intersections is even, so it's outside our polygon. And we can use the same technique with our input data over here. Let's say we look at that point and we go up 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, so all the way up in a diagonal. And then we see we have an intersection here we have an intersection here, and we have an intersection here, or we have 3 intersections. Number of intersections is odd, so it's inside our pipe. And if we look at that one, go up 1, 1, 1, 1, 1, 1. Draw a diagonal line here. We have 1 intersection, 2 intersections. Number of intersections is even. Oh no, it's outside our pipe. Okay, so that's how I solved part 1 and part 2 of day 10. You see, for at random code, it's really important to know some basic algorithms. For example, you'll always need breadth first search and depth first search at some point. Usually there will be something with pathfinding, which will be a Dijkstra algorithms or an A star. And today it was the raycast stuff. I've seen on Reddit that some people solved it with a shoelacing algorithm. I have no idea how that works and what it is. I look into it because it seems quite interesting. If you're interested in the code, check out my GitHub repository. If there's anything you didn't fully understand, leave me a comment. If you enjoyed my explanation, I'd really appreciate if you gave it a thumbs up. And see you tomorrow.